In the last segment, I talked about the difference between the population standard deviation and the sample standard deviation. Remember, the population standard deviation is a parameter because it's taken and calculated using all of the data from the entire population, and we designate it with Greek letters. So the Greek letter sigma is how we designate the population standard deviation. Its formula is a little bit different than the sample standard deviation because for standard deviation, when you have the entire population, when you're figuring out and working through the process with your data values minus your population mean quantity squareds for each data value and adding them up, after that you divide by n, the total number of values in your population. Now for the sample standard deviation, the statistic, we denote that with the English letter S to show that it's just done from sampling the sample of information. And when we show the formula that's the definition formula, we will still take each individual value and subtract off of it its sample mean, quantity square that, add those up, and then divide by the number in our sample minus 1. So the formulas differ a little bit to adjust for the fact that you just have the sample for your standard deviation instead of the entire population. Now the sample standard deviation formulas, there's two different forms of it. They will calculate the same number for you for a given sample data set, but one form really describes what's going on. See, the sample standard deviation tells you the average distance the data values are away from the mean, the center of the data set. But when I have a data set that has a mean that is a non-terminating decimal, this can get pretty cumbersome, carrying those decimals all along at each of the stages. So using the properties of summations and squaring out the binomials and working with that, there is a formula that is given that actually helps you do the computation of the standard deviation so that you don't have to deal with all of those decimals. But it's an equivalent formula, so you'll still get the same answer. We've done an example using the definition formula for it, so now let's use the computational formula. Now notice in the computational formula, which I've written over here as well, there's no x with a bar over it. So I don't calculate the mean first when I'm using this form of the standard deviations formula. I just have the sum of the x's in the parentheses that's being squared in this portion of the formula, and then the sum of the x squareds in this portion. So I need a column where I'll write down the individual x's, and I need a column where I'll write down the squares of the individual x's. So the individual numbers that our data set has is 1, 1, 5, 9, 9. Now I'm going to square each of those numbers. 1 squared is 1 squared is 1, 5 squared is 25, 9 squared is 81, and 9 squared is 81. Now if I add up all of the individual numbers, that's symbolized by add up or the summation of the individual data values from your sample. So here when I add them up, I have 1 plus 1 plus 5 plus 9 plus 9, that's 10, plus 10 is 20, plus 5 is 25. I also want to add up the squares of the x's. So this is the summation of x squared. And when I add each of these up, I get a total of 189. So I have 81 plus 81 is 162, 63, 64, and 164 plus 25 is my 189. Now I'm going to place these in the formula for my sample standard deviation. S is equal to the square root of, let's write out our fraction bar. Here, this is the square of the x's and then they're added up. So that is where you've squared the x's first and then you added up all of those squares of the x values. So that's the 189. Minus, and then we're going to make a small fraction bar there. In the numerator is the sum of the x's, 25, and I'm going to square that number. So 25 squared in that numerator. In the denominator, it's n for this little fraction, and that's the number of data values you have. 1, 2, 3, 4, 5. And then in the overall denominator, it's the number of data values you have in your sample minus 1. So 5 minus 1 is 4. Now we need to follow our order of operations for this. S is equal to the square root of, I have my 189 still, minus, I'm going to square 25. 25 squared is 625. And that's divided by 5 in a small fraction there. And the overall thing is divided by 4. Now I need to simplify my numerator and then do the division and then take the square root. So 625 divided by 5 is 125. So I have the square root of 189 minus 125 all over 4. Well, 189 minus 125 is 64. So I have the square root of 64 over 4. And 64 divided by 4 is 16. And the square root of 16 is 4. So again, we got our sample standard deviation for this data set to be 4. The same value we got for the standard deviation of this sample standard deviation of this data set when we used the definition formula for our standard deviation.